Hello everyone, welcome to Sunya IAS and welcome to lecture number 3 of Modern Algebra of Mathematics Optional UPSC CSE, which is asked in your paper 2 section A. So in the last lecture, we did our some questions on the groups and binary compositions, okay, and we checked if the sets were forming groups or not, and then we did some theorems, okay, and apart from for that was remaining, that was laws of integral exponents that we'll be taking up right now. All right. Now it's basically theory and we'll be using basic mathematical induction to prove a few of the given formulas, and then we'll move towards finite groups, right? Chalo. Let G be a group with binary operation dot, then by closure property A dot A dot A dot A up till A dot A dot A n times will always belong right. Also, as associativity follows, order of consequences, order of order of the occurrence is of no consequence. Okay, then with respect to, this is WRT, with respect to, all right, with respect to the group the following postulates follows. Okay, first one is a raised to the power 0 is equals to e is always the identity element. Here we are talking in terms of integral exponents when it is raised to a power of some integer. Okay, so the element of any group. So that means if I'm raising any element to the power of 0 in a group, then it necessarily has to be equal to e, which is going to be the identity element of the group. Clear? Now second one is that a raised to the power 1 is always going to be a. That means that any element raised to power 1 retains its value. Okay, now you might feel that these things are a bit redundant, they don't need to be specified, right? But the thing is that when you abhi aap yahan pe dekh rahe ho, you are taking a as a number only, but there are groups where elements are something totally different. They are symmetries, they are reflections, rotations and whatnot, vector components, all of these things are there. So in that case also these things apply. That means the law of integral exponents applies when we talk about a group. So that is why we are writing these things. All right, then you have, or I should take it to the next slide. Then you have third one is for n greater than equals to 1, a n plus 1 can be written as a n dot a raised to the power 1. Then finally fourth we have for n is greater than 0, a raised to the power n to the power minus 1 is equals to A inverse to the power n, which is nothing but A inverse multiplied n times. Clear? So this is true for all the elements which belong to a. Clear? Now we have certain similar kind of formulas ही कह लो इनको, and these we are going to prove by using mathematical induction. Now first one says that if G is a group and A belongs to G, then for any n positive integer, A dot A to the power n is equals to A to the power n dot A. Why? Because eventually it is going to become A to the power n plus 1 only, right? Chalo, let's take the first one and prove it. Now if you remember what we used to do in mathematical induction, first we used to assume a statement. So let Sn be A dot A to the power n equals to A n dot A, right? Now for n equals to 1, first we'll check if the statement holds for the value of n equals to 1. So it is going to give me A dot A to the power 1 equals to A to the power 1 dot A. So it clearly holds, right? I can write it as A dot A equals to A dot A. So S1, this implies that S1 is true, right? Now what is the next step? Next step is that let Sk be true. Any arbitrary value of the integer n I'm taking, that it has to be true for n k, right? So this implies that A dot A to the power k equals to A to the power k dot A. Now for Sk plus 1, what is Sk plus 1 going to be? It is going to be A dot Ak plus 1, right? Can I write it as, now I am just taking the left hand side, right? Obviously abhi मेरे को prove करना है इसको, so from here I have to go till here for k plus 1. Clear? So can I write it as A dot A k dot A? I can split it into 2, right? Now what is the value of A dot AK? A dot AK I can write it as AK dot A dot A, right? A dot AK ka value I can put from here. A dot AK is equals to AK dot A. So this I can write it as, if I name this equation as 1, I can take by 1, I can say that this is going to be true, and this can be written as AK plus 1 dot A. So AK plus 1 is equals to A raised to the power k plus 1 is equals to A. So this implies that Sk plus 1 is also true. Let me write the conclusion in the next page. So this implies that Sk plus 1 is true, right? So this implies that Sn is true for n belongs to natural number. Yeah? So this implies that हमने अपना पूरा जो statement है वो true prove कर दिया. Now the second one says that A raised to the power n and A raised to the power minus n are inverses of each other. Again by using what? Induction, we can solve it. So this is going to be by using mathematical induction. Let Sn be A raised to the power n dot A raised to the power minus n equals to A raised to the power minus n dot A raised to the power n equals to E. यही होगा statement. Why? Because we are saying in the statement that a raised to the power n and a raised to the power minus n are inverses of each. Clear? Now, for n equals to 1. For n equals to 1, a raised to the power 1 dot a raised to the power minus 1 equals to a raised to the power minus 1 dot a equals to e, which is nothing but e equals to e equals to e. So this implies that S1 is true. Any problem till here? Right? Now, let Sk be true. Right? Ab Sk be true, that means a raised to the power k dot a raised to the power minus k equals to a raised to the power minus k dot a raised to the power k equals. And this is a true statement, right? This we have assumed. Now for Sk plus 1, LHS is going to be a raised to the power k plus 1 dot a raised to the power minus k plus 1. Now, can I write it as a raised to the power k dot a raised to the power minus k dot a raised to the power minus 1? Right? It can be written like this. Now, what I want is, I want this minus sign to shift over here. So I want that this whole part should come on the left hand side, right? So what I can do is, I can take the value from this equation. So a dot a raised to the power k, wait a second, a raised to the power k raised to the power k minus 1. Here we are not getting any specific value that we can have here. Okay. Can we use anything from the previous statement that we did? So from here we have a dot ak is equals to ak dot a. Okay. See, first equation says a dot ak, a raised to the power k, is equals to a raised to the power k dot a, right? So can I write this as a dot ak dot a minus k upon dot a minus 1 by 1, right? Now what can be done? I can put the value of a raised to the power k dot a raised to the power minus k's value from here. So this is going to be nothing but a dot a raised to the power minus k dot a raised to the power k dot a minus 1. Now this is going to be what? It is going to be identity, right? A raised to the power minus k dot a raised to the power k. These two are going to be inverses. So this means that this is going to be a inverse, which is eventually going to be equals to e. Similarly, a raised to the power k plus 1 dot a raised to the power k plus 1 will come equals to e. मतलब आपने a raised to the power k plus 1 dot a raised to the power minus k plus 1 prove किया. From here you can similarly prove that a raised to the power minus k plus 1 dot a raised to the power k plus 1 is going to come eventually equals to e. So this implies that a raised to the power k plus 1 dot a raised to the power minus k plus 1 equals to a raised to the power minus k plus 1 dot a raised to the power k plus 1 e. This implies that a raised to the power k plus 1 and a raised to the power k plus minus k plus 1 are inverses of here. This implies that sk plus 1 is true. This implies that Sn is true for all n belongs to, right? Chalo. Moving on, let G be a group and A belongs to G and n is any positive integer, then you have a raised to the power m dot a raised to the power n is equals to a m plus n. These are going to be fairly easy. Okay, आप क्या करोगे, आप m को as a variable ही रहने दो, n को take the sn वाला n, right? And then you can take the statement in form of sn and then prove using the mathematical induction. You can pause the video right here and try them by yourself, or you can follow along, right? So first one is, let me change n's color. First one is a raised to the power m, a raised to the power n equals to a raised to the power m plus n. Now see, let Sn equals to or implies a raised to the power m dot a raised to the power n equals a m plus n. Now for n equals to 1, n equals to 1, what is it going to give me? Am dot a equals to am plus 1, which is nothing but am plus 1 equals to am plus 1. That means the given statement is true for n equals to 1. So now let Sn or Sk be true. This implies that am dot ak equals to am plus k, right? Now for Sk plus 1 is going to be what? Am dot ak plus 1 is equals to am dot ak dot a, right? And the value of am and ak I can take from here, right? So I can write it as am plus k dot a by 1, right? And which is going to be equal to am plus k plus 1, right? So this implies that Sk is true. That means Sn is true for all n. Clear? Very easy. Let's take the next one, that is am to the power n is equals to amn. Okay. So Sn is what? Am to the power n equals to amn. I hope I've written correctly. Yeah. For n equals to 1, am to the power 1 equals to am, which is nothing but am to the power am. Am to the power m is equals to a to the power m, right? So this is true. S1 is true. So let Sk be true. If Sk is true, that means a raised to the power m to the power k equals to a raised to the power mk. Now for n equals to k plus 1, that is Sk plus 1 is going to be a raised to the power m k plus 1. So this can be written as a m, wait a second. Okay, we can split these powers. So am to the power k dot am to the power 1, right? Now am, that means a raised to the power m to the power k, I can write it as a raised to the power mk from 1. This implies that this mk plus m, okay, and this is a raised to the power mk plus. Okay, so this is what we wanted to prove only. So a raised to the power m to the power k plus 1 equals to a raised to the power m k plus 1. Clear? Chalo, let's take the next one. That is ab to the power n equals to an a raised to the power n, b raised to the power n, where g is abelian. Okay, so this we have to keep in mind that g is abelian. Okay. All right. Let Sn be. Okay, this is Sn. Now, we'll just check for n equals to 1. For n equals to 1, we have ab to the power 1 equals to a to the power 1 to the power 1, and we have ab equals to ab. This implies that S1 is right. Now, let Sk be 2. So this implies that ab to the power k equals to a raised to the power k, b raised to the power, right? Now, Sk plus 1 going to be what? A b to the power k plus 1. Okay. So what we can do is we can write it as ak plus 1 dot bk plus 1, right? Then we can write it as a raised to the power k dot a dot b raised to the power k dot b, right? What do we need here? We need a raised to the power ab raised to the power. So eventually we need a raised to the power k plus 1 and a raised to the power k plus 1, b raised to the power k plus 1. Okay. The problem here is that we cannot write it as this. ये तो सीधा ही proof होगा. Wait. We can write it as ab to the power k dot ab, right? So this is going to be a to the power k, b to the power k dot a dot b, right? Now, since it is abelian, can I switch these two values? What is abelian? A operation b is equals to b operation a, right? So this is going to be a raised to the power k dot a dot b raised to the power k dot b. So from here I can say that a raised to the power k, where am I going to use this value? That is what is confusing me here. So this is this, and a raised to the power k. Then problem is that we don't need this statement here. ab to the power k, okay, ab to the power k dot ab. Oh, okay. Okay, for now we can take it as a raised to the power k plus 1, then b raised to the power k plus 1. Okay, so this says that a s k plus 1 is true, right? So this implies that Sn is true for all n belongs to natural number. All right, let's take up the next one. Now, okay, one more is there, I guess. E raised to the power n is equals to e. Okay, this should be fairly easy, I guess. Fourth one is raised to the power n equals to e. So Sn equals to this only. Okay. N equals to 1 is e equals to e. S1 is true. And then you will have let Sk be true. So e raised to the power k equals to e. Let this be equation 1. I guess here, okay, by 1 we are able to write ab to the power k by this only, no, 1. That is what I was thinking at that time, that where are we using the assumption, right? So from using this, we are able to write that, and then abelian group leke yahan pe we are able to switch these places, and then we are able to prove it. Yeah. Chalo. Now this implies that sk plus 1 will be e raised to the power k plus 1 equals to. Now can I write it as e raised to the power k dot e? So this is going to be e raised to the power k is what? E only. So e dot e is eventually going to be e, and this I have taken from 1, right? So s k plus 1 is true. This implies that s n is true for all n belongs to natural numbers, right? So here we have proved all of the postulates. Now let's take up the next unit, that is groups of finite order. अब आपका सारा जितना भी extra चीजें थी that we have covered. Now we are going to start the repository thing that I was telling you about in the first lecture, right? So let's take up the very first operation that we will be understanding first. Now what is this? Addition modulo. Addition modulo is nothing but it is a binary operation where you are taking two elements or two integers, and then you are dividing it by an integer n or m, whatever you want to call it. But the answer is going to be, आपने add करा, and then the answer is going to be the remainder you are getting when you are dividing a plus b by m. Here, for example, let's say let a equals to, let's say 7, and b equals to 5, and m equals to 4. Let's take 3. Okay. So when I'm applying addition modulo, the symbol is addition modulo m, which is what here? Addition modulo 3, right? So when I'm applying it between two numbers, that is two integers, 7 addition modulo 3 plus 5 equals to, again it is going to give 0 only, chalo theek hai. This is going to be 12 divided by 3. What is the remainder when I divide 12 by 3? That is 0. So basically the answer to 7 addition modulo 3 plus 5 is equals to 0. Now let us take something else. 7 addition modulo 5 plus 9. So this is going to be 16 by 5. What is the remainder? 1. 13 plus 7 and addition modulo, let's take 7 only. So this is going to be 13 plus 7 is 20. What is the remainder? 6. Alright. So addition modulo is a binary operation which gives you the remainder of a plus b. Here. Now you can read the basic definition. If a and b are integers, m is a fixed positive integer, then addition modulo is defined as this, and where r is going to be less than or equals to m, है ना? And r is the least non-negative remainder when a plus b is divided by m. Now why are we studying this binary operation? Is because the introduction of a new group, that is group of residue, you might have seen in the previous slide as well. Now this addition modulo m forms group with the set of the form Zm. Now what is Zm? Zm has elements starting from 0, 1, 2, 3 up till m minus 1. Clear? So if you have, let's say, addition modulo 6, so what is the set that is going to form a group with respect to this binary operation? It is going to be Z6. That is 0, 1, 3, 4, 5 and not 5, not 6, just 5. Okay? M minus 1 tak you are going to take it. What is the order of Z6? Is 6. Clear? Now, let's take an example. Let's say Z4 addition modulo 4. What are the elements going to be like? 0, 1, 2, 3, right? Now, if you want to check the group, that if this algebraic structure is forming a group, we need to check for closure, we need to check for associativity, and we need to check for identity element, and then we need to check for inverse, right? Now, we do that by the help of composition table. Okay? What are you supposed to do in composition table? आपके जितने भी elements हैं in the set, okay? You are going to write it in the row and the column here. This is 0, 1, 2 and 3. 0, 1, 2 and you are going to write the operation here. Clear? अब यहाँ पे आप क्या करोगे? You are going to operate each element and you are going to prepare the table. So 0 plus 0, 0, 1 and 3, right? Similarly here, now 1 plus 1 is 2. 2 when divided by 4 is again going to leave the remainder 2 only, right? 1 plus 2, 3. But 1 plus 3 is going to be 4. 4 when divided by 4 is going to leave remainder 0. So this is 0. Now 2 plus 1 is 3. 2 plus 2 is 4, that is 0. Plus 3 is 5, that is 1. 3 plus 1 is 4, 0, 5, 1, plus 3, 6, that is. Now, first property is your closure property. Whatever the elements are there in the composition table belong from the set itself, that is Z only. अब देखो सारे elements are 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3 and 0, 1, 2, 3, right? So that means closure property is satisfied. Then you check for associativity. अब associativity को check करने की you don't have to, there is no need to check it. Why? Because the base operation is what? Base operation is addition only. A plus B ही eventually you are doing and then you are calculating the remainder, right? So base operation is addition, so it is going to be associative as well. If you want, you can check it. आप कोई भी 3 numbers लेके you can check it. Then you have identity element. What is that one element with respect to which you are getting the element back again? That is going to be 0, right? So this is going to be your identity element. And now for inverse. Now for inverse, what do we check? For inverse, we are supposed to look for element with which, when this element is operated, I am getting the identity element as the answer. So for 0, I am getting 0 here. That means 0 is self-inverse because it is the identity element. Now for 1, I am getting 0 here. That means 1 and 3 are inverses of each other. And then 2, I am getting 2 here. So that means 2 is a self-inverse element. That means it is inverse of itself. And then finally 3 is inverse of 1. So you are getting identity element here. So this implies that identity 0 inverse is 0, 2's inverse is 2, 1's inverse is 3 and 3's inverse is 1, right? So here we can see that the group of residue, that is Zm, हम normally इसको we can call it Zm also. It is understood by itself that Zm is a group with respect to addition modulo m. Clear? Pay attention that these two values have to be same. Okay, Zm forms a group with addition modulo m. M and this value cannot be, these two values cannot be different. All right, chalo. Moving on, we have multiplication modulo. Similar to addition modulo, where we were adding the two integers, now we'll be multiplying two integers. Okay, so let's take some examples. 6 multiplication modulo let's say 10. So 6 sevens are 42. 42 when divided by 10 is going to leave remainder 2. Now 7 into 8, 56. So 56 divided by 10 is going to leave you with remainder 6. Now, can multiplication modulo form a group with respect to Zm? Let's check. What is Zm? 0, 1, 3 up till m minus 1. आप composition table when you'll be making, आप ये देखो, when you are multiplying all the elements by 0, you will get 0 here and 0 here. So there will be no unique inverses. आप ये देख लो, जैसे for 0 you are getting 0 everywhere, right? So आपका inverse का property is going to fail, rest of the all the properties also going to fail. So the conclusion is that multiplication modulo does not form or cannot form a group with respect to your Zm group, right? What it does form a group with is, if you remember our previous lecture, previous to previous lecture, we did one group, that is un, and un is nothing but x that means the collection of all the elements which are less than n and are co-prime to n. For example, if you take u10 here, so the elements are going to be 1, 3, 7 and 9, right? These all numbers are co-primes, and if you remember, the order of or the cardinality of un is given by phi n. Okay, phi n को कैसे करना होता है? Phi is p raised to the power k or p1 raised to the power k1 or p2 raised to the power k2. Then simply you split 1 to the power k1 and to the power k2 and apply the formula here, which is nothing but p1 k1 minus p1 k1 minus 1 multiplied by p2 k2 minus p2 k2 minus 1. अब यहाँ पे if I tell you to apply it in u10, so what is the cardinality of u10? यहाँ पे we are able to see that it is 4. So cardinality of u10 is going to be phi of 10. What is phi of 10? 5 into 2. This is 5 into phi 2. This is what? 5 to the power 1 minus 5 to the power 1 minus 1 and 2 to the power 1 minus 2 to the power 1 minus 1. This is going to give you what? 5 minus 1, that is 4, and 2 minus 1, that is 4 minus 4 into 1, that is 4, which is nothing but the cardinality of u10. Now, we know that un forms a group with respect to multiplication modulo n, right? So हम u10 का ही example ले लेते हैं and let's form the composition table with respect to it, and we'll be checking for closure property, associativity, then we have identity, then we have inverse, right? Chalo. Now with respect to 1, you're getting the same elements here, 1, 3, 7, 9. Now 3 3s are 9, remainder 9. 7 3s are 21, remainder when divided by 10 is going to be 1. 9 3s are 27, so the remainder is going to be 7. 7 3s are 21, 1 remainder. 7 7s are 49, 9 remainder. 63, 3 remainder. 9 3s are 27, 7, 9 7s are 4, 9 7s are 63. So this is going to be 3 as a remainder, 9 9s 81, 1 is the remainder. Clear? So we can see that all the components of the table lie from the set only or lie in the set only. So this implies that closure property is satisfied, right? Now to check for associativity, what is the underlying operation? Underlying operation is multiplication. So we know that multiplication of integers is always associative. Now for identity, with respect to which element we are getting all the elements back again? This is this. So existence of identity is also there. Now for inverse, we can check. Where am I getting 1 with respect to 1? That is 1. That means identity element is self-inverse, that we know. Now for 3. So 7 and 3 are going to be inverses of each other. And finally, 9 is going to be self-inverse, right? Okay. So we can write here that 1 inverse is 1. Then we have 3's inverse is 7. Then we have 7 inverse is 3. And finally 9 inverse is 9. Alright. Now we will move towards the dihedral group. अब इसको समझने से पहले let us understand, इसके definition पे नहीं जाना है, कुछ भी नहीं जाना है, just understand the concept, the basic concept behind it. What is a dihedral group? Basically, dihedral group is a group of, I should say, symmetrical transformation which are applied to a given shape such that the shape remains the same as before. Basically, बिल्कुल simple terms में, if I am taking an equilateral triangle whose all three sides are equal, right? So मैं इसको किस तरीके से rotate करूं such that it is going to look exactly the same. So it is going to be a symmetry. I can rotate it through an angle of how much? 120 degrees. अब वो 120 कैसे आया? Simple है, आप यहाँ पे axis लगाओगे and you are going to turn it through 120 degrees. It is going to give you the same exact rectangle, triangle. If you take, for example, if you take a hexagon, basically मुझे क्या करना है? I have to turn it through a minimum degree such that it looks the same, which is going to be this angle, right? And what is this theta going to be? Basically, अगर मैं यहाँ से start कर रही हूँ, if I'm starting from this point, what am I supposed to do? I'm supposed to turn it from here, then it will go here, then it will go here. I'm talking about this point, okay? And then it will go here, and then it will go here. It will take a total of 1, 2, 3, 4, 5, 6 turns to complete a full 360 degrees. 360 degrees करने में उसको 6 turns लग रहे हैं, right? That means I will have to rotate it through how much? 60 degrees. एक turn में I am rotating it through 60 degrees. So basically that is a symmetry. अब इसकी symmetry अभी हम बात नहीं करेंगे because primarily we talk about just 2 groups. आगे जाके when we will be talking about subgroups, we will be talking about D5 as well. But as of now, we will be dealing with the D3 and D4 only. That is nothing but your equilateral triangle and square, right? एक तो ये हो गया that I can rotate this shape through some angle such that it retains the shape. Second thing is I can reflect it along any axis. That means I can rotate it through the axis. कैसे? I can flip it. So this is going to be a reflection. Basically यहाँ पे if I'm placing a mirror, it is going to be the same shape on both the sides. So I can rotate, or if I can reflect it through the reflection through A axis. If this is A, this is B, and this is C, I can reflect it through A axis, I can reflect it through B axis, and I can reflect it through C axis as well. So there are two types of symmetries possible. First one being a rotation and the second one being a reflection. Here, now majorly two types of symmetries are there. First one is rotation and the second one is reflection. Here, now what is the simplest transformation? What is the simplest transformation I can do to a shape? It is doing nothing, which is what? Rotating it through 0 degrees, right? So if I rotate a shape through 0 degrees, it is going to be exactly itself, and it is going to be the simplest transformation, which is nothing but your identity element. So R0 is the identity element when I talk about the group that is your dihedral. Here, now if you want to see the proper definition, it is this, that our dihedral group is the group of symmetries of a regular polygon which includes rotations and reflections, and this is the layout description in terms of both rotation and reflection, how the elements of the groups are formed. It is given here. Now the important point here is that in Dn, any Dn, we are talking about dihedral group, theta is equals to 360 divided by n. So that means when I'm talking about a triangle, it has 3 sides, right? I'm talking about the symmetries of a polygon which has 3 sides. So I'll be talking about the theta in terms of 360 divided by 3. So for D3, my theta is going to be equals to 120, right? Same case for D4. So D4 is going to be the collection of symmetries of a regular polygon, that is a regular square. So for square, I'm going to have theta is equals to 360 divided by 4, that is going to be 90. Clear? Now, the rotations are done counterclockwise. This is the most important thing. Counterclockwise is nothing but your anti-clockwise. The opposite of clockwise. How does your clock move? This is your clock. The needle moves this way. The hour hand and the minute hand move clockwise, that is this direction. But whatever rotations we are going to do in the symmetries, it is going to be counterclockwise, which is nothing but anti-clockwise, that is opposite to what a clock moves, right? Chalo. Now let's take up construction of T3, which is what? The group of symmetries of a triangle. So naturally the triangle has to be such that all 3 sides are equal, right? So this is A, B, C. What is the easiest transformation? That is rotating it through 0 degrees. So it is going to remain exactly the same, right? But then what is the theta going to be? Theta is 360 divided by n, that is 360 divided by 3 in this case, that is 120 degrees. So when I'm going to make a rotation of 120 degrees but counterclockwise, that is anti-clockwise, my triangle is going to look of the form A, B and C. I have rotated this shape in counterclockwise direction. So A vertex is going to shift one place, and B is going to shift one place, and C is going to shift one place. Now finally, I will have A, B and C. Now I am rotating it through 120 degrees. I can rotate it through 240 degrees as well, right? Even then, अगर मैं एक बार इसको flip कर रही हूँ, if I'm rotating it through once, then again I'm rotating it through 240 degrees, right? So if I'm rotating it through 240 degrees anti-clockwise, what is going to happen? A is going to jump 2 places from here to here. So it is going to look like A, B and C. Clear? Now finally, if I take the next multiple of 120, that is going to be nothing but A, B, C, and I rotate it through 360 degrees anti-clockwise, it is going to be nothing but A is here, so it is going to switch 3 places. So 1, 2 and 3, it is going to come back here. So we can say that this is nothing but R0. So distinct elements or distinct symmetries or distinct rotations in a D3 group are R0, R120 and R240. And R360 is again equal to what? R0. तो उसके बाद जितने भी multiples आते रहेंगे, they will be similar to one of these elements. Clear? I'm just going to remove them. Now these were what? Your rotations. Now we will be talking about reflection. Now reflections can happen along axis, which are reflection along A axis or A vertex, you can say. So in which A is going to remain intact, but B and C are going to switch positions. Then similarly, the reflection can happen along B vertex or B axis, and this is called FBB, which is going to be what? B is going to remain intact and A is going to be here and C is going to be here. And finally, it can happen along C axis, that is FCC, which is nothing but C is going to remain in its place and B and A are going to switch position. Okay, so these are all the rotations possible and these are all the reflections possible. Now, what does our D3 look like? D3 has R0, R120, R240, FAA, FBB, F, right? So from here, can I say what is the order of D3? That is 6. That means 2 times of 3. So order of Dn equals to n. Clear? Whatever Dn you are taking, the order or the number of elements is going to be double the n, right? Now, one important thing here is, what is the operation? What is the operation or the binary operation that we are going to use for Dn to be a group? That is nothing but your composition happening, or composition of functions, right? These are eventually functions only. Clear? अब यहाँ पे usually fog is equals to gof, that we know, fog is equals to g of f, right? But here that is not the case, right? Whenever you are applying, wait a second, आप यहाँ पे देखो, if I am applying R120 with R240, what is it going to be? It is going to eventually R360, which is nothing but R0 only, that is R0, right? If I'm adding R0 and R240, which is again R240, R0 and R120, which is again R120, right? Similar is the case with reflections. But what happens when I mix these two? When I'm operating one rotation with one reflection, it is going to be what? Let's take for an example R120 and FAA, right? So if I'm taking, let's say A and C, so I'm applying FAA first, right? पहले आप आगे वाला function लगाते हो, right? So FAA I'm applying, so it is going to be, A is going to be intact and C and B and C are going to switch places, and then you are going to apply R120 anti-clockwise, and that is going to be what? A, C and B, right? Now if you notice what has happened between this diagram and this diagram, from here till here C has remained intact. C is in its original position and A and B have switched places. That means when I have operated one rotation and one reflection, I am getting a reflection. This is what? This is FCC, right? Now let me switch it the other way. Let's take green, or let's take yellow. Let's do FAA and R120. Now what is going to happen? A, B, I'm applying R120, right? Now this is what? A, B and C. Now one thing to note here is, whenever you are using composition of functions in a dihedral group, although this is not going to be used आगे जाके, but you should know how these things work. कि आपका जो function है, composition of function है, it is not commutative. That is why dihedral group does not form an abelian group for order greater than 2. Alright, यहाँ पे क्या होता है? One thing to note is, whenever you are applying first rotation then reflection, once you have applied the rotation, the reflection is applied on the original position. That means, what is the original vertex? A. So अब यहाँ पे you are not going to apply the reflection along this axis, but you are going to apply it along this axis. Clear? Let me remove it. So original axis ये था, so reflection is going to be applied along this axis only. So when you apply FAA here, you are again going to get C is going to remain intact, and then B and A are going to switch positions. Now if you check between this and this diagram, what has happened? B has retained its position, but A and C have switched places. So this is nothing but FBB. So again, what is happening? When I'm applying a reflection and a rotation, I'm getting a reflection. So how to know that when applying one reflection, one rotation, or two rotations, or two reflections, what am I going to get? So for that, what you're supposed to do is, you're supposed to assume that rotation is positive and reflection is negative. Negative मतलब कुछ नहीं है, subtraction की तरह लेना है, right? ऐसा नहीं है that reflection is a bad thing, so you have to take it negative. So it is again going to be negative. Why? Because plus minus is minus when it comes to multiplication. So this is reflection, right? If you take two rotations, that is going to be plus plus, right? So again you are getting a rotation only. And finally, if you take two reflections, if you are going to take, again you are going to get rotations. Why? Because minus minus gives you plus. Okay? Now, reflection plus rotation is again going to give you reflection only. That I'm not writing here, that has been written here. Now, just note this, that bhale hi rotation plus reflection is giving you reflection, but that same reflection plus rotation is not going to give you the same reflection as the answer. Why? Because we just saw here that R120 FAA is not equals to FAA R120. That means they are not commutative. That means DN in general is not an abelian group. Clear? Now let's see the composition table for D3. I would want that you do not see it at first. You can pause the video here. Try to make all the compositions right here abhi, ताकि it gets very clearly etched into your memory. It is, you know, right here, and अगर आपको कहीं operations करना है, so you are very easily able to understand what the group is doing. आप D4 के लिए नहीं बोलूँगी मैं आपको, D4 के लिए I will be giving you the group the composition table straightforward, but at least to do this much so you are well versed with the idea of the group. Clear? For reference, this is the composition table for D3. Now we will be talking about D4. Now let's see the construction for D4. What is the theta going to be? Theta will be divided by 4, that is 90 degrees. So for one symmetry, you are going to rotate the shape through 90 degrees, right? First, we are talking about rotations. This okay, these are just letters. Usually this is the common notation that we take for representing D4. Okay, आप ABCD भी ले सकते हो, there is no problem in that, right? First one is obviously R0, right? So this is rotation through 0 degrees. So again I'm going to get the same symmetry. Then next one we have R90. So for 90, what is going to happen? One places are being shifted by each vertex. So anti-clockwise. So this is going to be P, W, B, and then we will have P, W, then rotation through 180 degrees. This is what? P will shift 2 places. Similarly, W will shift 2 places, B will shift 2 places, and G will shift 2. So this will be P, P, W, and B, right? And then finally we have R, what is it? 270. Okay, will shift 3 places. So this will be P, 1, 2, and 3, right? W and now then next one is going to be R 360, which is what? P is going to shift 4 places. So this is P, W, and B, which is essentially the same thing. That means only 4 unique rotations are going to be there when we talk about. All right. The rotations are R0, R1, not 120, R90, R180, R2, right? Now, how do reflections take place in a D4? Reflections are either along the horizontal axis or the vertical axis, or they can be along the main diagonal, or they can be along the secondary diagonal. E, W, and B, W, and B. So what happens is, when I am reflecting this given shape along an axis, W and B come here and P and G come here. Then similarly, vertically, these are going to flip. So this is GB and this is PW, right? Now here, and these are known as reflection H, reflection, that is horizontal reflection and vertical reflection. And then you have reflection along the diagonal, and then finally you have along the secondary diagonal. So P and B are going to remain intact. W and G are going to switch places, right? Similarly here, W and G are going to remain intact, and B and P are going to switch places. So what are the reflections? The reflections are H, E, D and D dash, right? Now what is the final composition for D4, or the final elements of D4? They are R0, R90, R180, R270, R60 is again R0, right? Uske baad whatever the multiples are 90 are going to be there. They are going to be similar to these rotation zones. And then you have H, B, D and D dash, right? Now again the same thing is going to follow. Rotation plus rotation is again rotation here, rotation plus reflection or multiplied by reflection is reflection. And reflection multiplied by reflection gives you rotation. Achha, one thing I forgot to discuss is that let us notice if when I'm combining two rotations, am I getting all the rotations? Ab dekho, yahan tak there are all rotations. So all the elements till here in this box are rotations only, right? When I am combining what? One reflection and one rotation, I am getting reflection, reflection, rotation, reflection. So for all these, the elements are reflections only. These are reflections only, right? But when I am combining two reflections, what am I getting? Again I am getting all the rotations. So from here you can prove or you can verify that when you are applying two rotations, you are going to get rotations. When you are applying two reflections, again you are going to get rotations. And when you are going to mix both of them, that is one reflection, one rotation, or one rotation and one reflection, again you are going to get reflections. Clear? Now let's look over to the composition table for D4. Now this is D4. Now again the same property holds. If you notice, when you are applying rotations, rotation on rotation, you are all getting rotations only, right? And when you are applying reflections with reflections, again you are getting rotations, right? When you are mixing the two, when one reflection and one rotation, you are getting all the reflections, right? And same property holds here as well. But the product is always, or the answer is always either a reflection or a rotation. It can never go around that way, right? So that means aapka jo DN hai, it does form a group with respect to composition of functions, and functions are what? Functions are rotations and reflections. Clear? Don't worry, we will be taking up proper proofs of the theorems. Theorems as in the groups that we are studying here right now. What I'm trying to do here is that I'm trying to get you acclimatized to the idea of these groups, what these groups are. सीधा अगर हम इनके proving start कर देते, the closure property and the elements and all that, that would have been very confusing at start, right? So what we are doing here is we are getting to know the groups better. So what kind of elements are there? After this we'll be studying about the order of the elements. Then once we are comfortable with each and every order of each and every element excuse me, once we are comfortable with every element's order, then we will be moving towards the proper proofs of the groups. Clear? All right. Now let's move over to the quaternion group. Now quaternion group is what? It is known as Q4 or it is known as Q8 as well. The elements are of the form plus minus 1, plus minus I, plus minus j, plus minus k, right? And if you remember, I, j and k, they used to operate in this manner, where I square equals to j square equals to k square equals to minus 1, right? And I to the power 4 equals to j to the power 4 equals to k to the power 4 equals to plus 1, and ij equals to minus of ji equals to k, then jk equals to kj, negative of kj equals to I, and finally ijki. So ki equals to minus of ik equals to. So this is a quaternion group. And what is the binary operation? Binary operation is nothing but your usual multiplication. Here the composition table to this group is rather very large. You can see that here. So आपके वही elements है repeat हो रहे हैं. The basic concept is this only, that I square is equals to minus 1, j square is minus 1, k square is minus 1, and I to the power 4, j to the power 4 and k to the power 4 are equals to 1. That means what can be the order of this element? All of these elements are of order 4. Yeah. And then you have these relations when these elements react with or they interact with each other. So this is going to be the composition table. You can make them by yourself. All right. Then you have Klein's group. What is Klein's group? It is a group of order 4 and the elements are E, A, B and AB, which is also known as, matlab representation ke liye we call it C as well. Right. Now what are the properties? That A square equals to B square equals to AB square, which is C square only and which is equals to, that means the order of every element is 2 only, right? Also AB equals to BA equals to C, which is pretty clear from here only, and then BC equals to CB is equals to A, and AC equals to CA, right? So this is not a very important group. It's fine. We just have to know what are the elements like in a certain group. Now moving on, we have the set of all nth roots of unity where n is a fixed positive integer under usual multiplication of complex numbers. One very common example of this is when n equals to 4 and the group is 1, minus 1, iota and iota minus iota. Okay, so this is a group of fourth root of unity. But ये हमें बस ऐसे ही पता होता है कि what are the elements like, right? But how do we derive it? What is the formula behind it? That we will see right now. So starting from 1 raised to the power 1 by n can be written as 1 plus iota 0 raised to the power 1 by n. This can be written as cos 0 plus iota sin 0, right, raised to the power 1 by n. Then I can write it as cos 0 plus 2k pi plus iota sin 0 plus 2k pi, right? Okay, we can take it to the next slide, problem in that, and raised to the power 1 by n. Now by using, I hope why am I writing this is pretty clear, that the values of cos and sine repeat after intervals of 2 pi, right? By using De Moivre's formula, I can write the given expression as cos 2k pi upon n plus iota sine 2k pi upon n, where k equals to 0, 1, 2, 3 up till n minus 1. Why till n minus 1? Because the moment k takes the value of n and n are going to get cancelled, and we'll be left with cos 2 pi plus iota sine 2 pi, which is again nothing but 1 only. Clear? Chalo. Now let us see what are the different values of this expression when I'm going to take k's values from 0 to n minus 1, right? So I'm going to get cos, it is 2k pi, right? So this is 0 only, plus iota sine 0, which is nothing but 1 plus 0, that is 1, right? Then we have k equals to 1, cos 2 1 pi upon n plus sine, or I should just skip the part of 1. You can just write it as 2 pi by n plus iota sine 2 pi by n, and this value we can call it as r, right? Because इसी के terms में we are going to take the values of the next expressions, right? Then for k equals to 2, cos 2 dot 2 pi by n plus iota sine 2 dot 2 pi by n. This can be written as, if I again apply the De Moivre's formula, अगर मैं exponent से I can bring the value inside the angles, the same thing I can do reverse also. I can take this 2 in the whole power of the expression, right? So I can write it as cos 2 pi by n plus iota sine 2 pi by n whole to the power 2. Now this is what? This value is equals to r only. So this implies that this is r square. Clear? Now similarly I'll take k equals to 3. I'll get cos 2 dot 3 pi by n plus iota sine 2 dot 3 pi by n equals to cos 2 pi by n plus iota sine 2 pi by n whole, right? And which is nothing but r cube. Following the same pattern till k equals to n minus 1, I will be left with cos 2 dot n minus 1 pi divided by n plus iota sine 2 dot n minus 1 pi by n equals to cos 2 pi by n cos 2 pi by n plus iota sine 2 pi by n to the power n minus 1, which is nothing but r raised to the power n minus 1. Now these are all the distinct values which I am going to get of the nth root of unities, right? So what is my set going to look like? 1 r square r cube till r raised to the power n minus 1. Now ये हो गई आपकी एक जनरल टर्म में बात, right? We talked about one group right before when we started doing this formula or the derivation of this, which was fourth root of unity, right? Now let us derive that group using this formula here. So let n equals to 4. Now first we know that the first element is 1 only, that's fine, है ना? Let's do for r. So what was r? r equals to cos 2 pi by n plus iota sine 2 pi by n. What is the value of n here? 4. तो cos 2 pi by 4 plus eta sin 2 pi by 4, which is nothing but cos pi by 2 plus eta sin pi by 2. Now this will be 0 plus eta, which is eta, right? Now if I have the value of r, can I find the value of r square? R square is what? Eta square, which is nothing but -1, right? Then you have r cube, which is eta cube, which is nothing but eta dot eta square, which is eta dot -1, which is minus eta. So here I have the 4 distinct values of the 4th root of unities, which is 1, -1, eta and minus eta, which is the group that we talked about in the starting. Clear? So this is the group. And similarly आप कितने भी nth root of unity का group निकाल सकते. So this is 1, -1, then minus eta and eta. Clear? The proof of it, abelian है नहीं है, that all we'll be seeing afterwards. All right. Chalo, moving on. Now this is general linear, that is GLNF, the set of all n cross n invertible non-singular matrices over a field F. Now when we were discussing groups and doing questions on them, we saw that when we talked about the group of 2 cross 2 matrices, where we were taking the values from, I guess, integers or rational numbers, it was failing in one condition, where we did not have the inverse for it. Why? Because determinant was involved when we were calculating inverse of certain elements, that is certain matrices, right? So when we try to form a group of n cross n matrices, the one condition is that all the matrices have to be invertible. That means they have to be non-singular. And what is non-singular matrices? Jinka determinant is not equal to 0. Clear? Chalo. So let me define the group for you. This will be GLN F. F is nothing but just field se aap values le rahe ho for the matrices entries, right? So this is going to be Aij n cross n, where Aij belongs to the field F and determinant of A equals to is not equals to 2, or I should say that is, or we are talking about in general terms, no? So that's enough. Or you can write that A is invertible, okay? Or you can write A is non-singular. Clear? Singular matrices are those jinke determinants is equals to 0. Now, what is the order of group? Order of GLNF, it depends on 2 factors. One, when F is infinite, the order of GLNF is also infinite, right? But when F is equals to a finite field, okay, then the order becomes, the formula for that becomes order of GLNF when the field is finite it becomes p raised to the power n, q raised to the power n. Q raised to the power n, which is the order of, q is the order of the field. So q raised to the power n, n is what? The order of the matrices that we are taking, right? Q raised to the power n minus q raised to the power n minus 1, then q raised to the power n minus q raised to the power n minus 2, q raised to the power n minus q raised to the power n minus 3 till q raised to the power n minus q raised to the power n minus n, that is 0. And इसको आप क्या लिख सकते हो? ठीक है? So this is the order of the group. Though इतना use नहीं आता है ये बाद में, but it is good to know and it is good to have in your repository. Maybe a question can be asked देके step के order को, and they might ask some question on it depending on the n or the q or whatever, right? Now, the second type of group in this is SLNF, which is a subset or the subgroup of GLNF only. And how do we define it? It is SLNF equals to Aij n cross n matrices, and Aij belongs to fields, but the condition here is that the determinant of the matrices has to be equal to 1. Clear? यहाँ पे we are not, they are non-singular matrices, but the determinant has to be equal to 1. It cannot be any non-zero number. It has to be equal to 1. Now, again, the order depends on two things. First one, f is infinite. This implies that order of SLNF is equals to infinite only. When f is a finite field, let's say of the form ZQ, then the order of SLNF becomes same formula, just one difference. Q minus 1. So here we are just dividing by Q minus 1, and that is going to be your order of SLN ZQ. Clear? Moving on to the most important group when it comes to abstract algebra, I would say, is your SN group, right? Before getting into the theory, let us understand what is symmetric group and what kind of elements it does have, right? Chalo. So it is popularly known as symmetric group, or you can call it as permutation group as well. Now, first let's understand what is SN. Okay, when we are talking about SN, now this n is some natural number. Let's say n equals to 3, or before taking an example, n is a natural number, and SN is the set of permutation. Permutations are nothing but functions. What kind of functions? That we will see abhi. Okay. First, just understand, if I take n equals to 3, right? And if I just write the natural numbers 1, 2, 1, 2 and 3. In how many ways can I rearrange these three numbers? It can be written as, let's say, 1, 3, 2, or I can write it as 2, 1, 3. I can write it as 2, 3, 1, or I can write it as 3, 1, 2 and 3, 2, 1. Basically, in how many ways I can arrange these natural numbers is the idea behind permutation. ठीक है? ठीक है, fine. इतना आपको समझ में आया? Now, why do we call them functions or permutations? That we will understand now. Let's say I have 1, 2 and 3. Okay? And we saw that I can arrange them in certain manners, right? Now I'm arranging them. I'm taking one element from here. Element being this one arrangement from here. Let's say I'm taking 2, 1, 3. What did I do? I took three numbers 1, 2, 3 and I rearranged them in the form of 2, 1, 3. Clear? Now, if I call it as a function, these are what? The inputs, and these are what? The outputs. right? So can I say if this is a function f of 1 is giving me 2, f of 2 is giving me 1, and f of 3 is giving me 3, right? Basically, it is acting like a bijection. Why bijection? Because every element has unique image and all the elements of the set B are related. So basically, a permutation is a function from the set 1, 2, 3 to the set 1, 2, 3, which is a bijection. Clear? Now, if I'm talking about the collection of all the functions, all the 1, 1 onto functions possible in a group where there are n natural numbers, what are the possible number of elements that this group is going to have or this set is going to have? So if I'm talking about S3, यहाँ पे I saw that there are 6 possible arrangements, right? एक general term में अगर मैं देखूं, तो I have 1, 2 and 3 and I have to place them in 3 places, right? Now if I take 1, how many choices does it have? It has 3 choices. It has 3 choices, right? If I take 2, if I have placed 1 in one of the blanks, then it leaves me with 2 choices for 2. So I am left with 2 choices, and finally 3 has only 1 choice. So the total number of arrangements are going to be 6, which is nothing but your 3 factorial. So order of Sn is nothing but n factorial, which is basically the number of arrangements possible for n natural numbers. Clear? Now, what do we know so far about Sn group? Sn group, first, that basically it is the rearrangement, or I should say it is the set of all possible rearrangements of n natural numbers, right? Then Sn has a total n factorial elements. That means basically n factorial arrangements are possible, right? Now, we are talking about Sn being a group. For group, there has to be a binary operation, right? So that gives us the question that what is the binary operation here? Now, since any element that belongs to Sn is a bijection, that means the binary operation is nothing but composition of functions. Right? Now, how do we multiply two permutations? Basically, how do we operate two functions which are permutations that are elements of the group Sn? Let's take an example. Let f equals to 1 and let's say g equals to 3, 1 we can take. Okay? So these are two elements of the group S3. Clear? Now I want to multiply these two, or basically I want to see how elements of Sn behave or interact with each other. So if I'm going to calculate Fg, again it is going to give me a bijection only, right? That means there has to be inputs, and for them the respective outputs are going to be there. Now f of g is what? F of gx, right? So I'm going to start from g here, right? So if 1 is the input for G. It is giving me output as 2, which is going to be the input for F. That means from here I have to go here. So 1 is being mapped to 2 and 2 is being mapped to 1. So eventually fog is going to give me, or F of G is going to give me what? 1 only as the image of 1. Then similarly 2 is mapped to 3 and 3 is mapped to 2. So I'm getting 2 here. 3 is mapped to 1 and 1 is mapped to 3. Now you can see that each element has been mapped to itself only, right? And this is your identity element. Why did we get an identity element here? That is a totally different thing, right? But what is important here is to pay attention as to how we are calculating f of g and g of f. Clear? आप जब भी दो permutations को multiply करते हो, whenever you are multiplying two permutations, just be very careful. Let me write it here. Let's say you have 1 and 4 and 4, 1, 2, and you have same thing. No, I want it such that no element is being mapped to itself. Okay, so let's say I'm multiplying these two. Clear? So what is going to be the answer here? 1, 2, 3 and 4. So I'm going to start from here. So 1 is mapped to 3 and 3 is giving me 2 here. So 2 is mapped to 1, 1 is mapped to 4. 3 is mapped to 4. So 4 is mapped to 3. And finally 4 is mapped to 2 and 2 is mapped to 1. So basically this is f of g. That means if this is f, this is g, this is fg, right? Now if I'm supposed to calculate g of f, now पहले I will start taking the values from f here. So f से start करेंगे. 1 is going to 4, 4 is going to 2, 2 is mapped to 1, 1 is mapped to 3, 3 is mapped to 2, 2 is mapped to 1, and finally 4 is mapped to 3 and 3 is mapped to 4. Now can you see that the set of images is completely different, right? Here we were getting identity element. So अगर हम उल्टा भी करते तो again हमको identity element ही मिलता है यहाँ पे. But you can clearly see that when I have taken another example, f of g is not equal to g of f. So this is going to be generally true, right? When it is going to commute, that we are going to see in the next example. But for now, we know that f of g or fg is not equal to gf generally, right? Now, another point is that when we write these bijections or these functions in this form, that is 1, 2, 3 and then their images, then 1, 2, 3, 4 and then their images, it's fine for let's say S4, S5, but what of the elements of S10, S12, S25? So it becomes a bit tedious when we try to write these in this form, right? So then comes your concept of R cycles. Now what is an R cycle? Let's say you have S3 group, right? And then you have the permutation as 1, 2, 3, 3, 1. Yeah. So what you're going to do is, you are just going to try to form a cycle. Cyclic, R cycle लिखा हुआ है, cyclic permutation भी कहते हैं इसको. You are trying to form a cycle and you're going to represent it, this function in just one line. How? See, 1 is mapped to 3. So 1 is mapped to 3. 3 is mapped to 2. 3 is mapped to 2. And then 2 is mapped again to 1. Now this you should be able to visualize that this permutation can be represented as this, where 1 is being mapped to 3, 3 is being mapped to 2 and 2 is again being mapped to 1. So cycle क्यों कह रहे हैं हम इसे? It doesn't matter if I start with 1 here. Even if I start with 3 here, I'm going to get the same permutation here. आप देखो, if I start with 3, so 3 is going to 2 and 2 is going to 1. I'm getting what? 3, 2, 1. The images for the respective elements are same. Same thing you can do with the 2. The 2 is going to 1 and 1 is going to 3. The order is same, 1, 3, 2. 3, 2, 1. After 1, 3 is coming. After 1, 3 is coming. After 3, 2 is coming. After 3, 2 is coming. Okay. So now do you get the idea that why we are calling them R cycles? Again, one more thing you can see. 1 is being mapped to 3 and 3 is being mapped to 2. If I write them like this, it does not matter that which element comes first. The value of this R cycle is always going to remain the same only, right? Chalo. Now this is about S3. Now let's take an example from S4 or S5. Let's take S5 and let's take an element 1, 2, 4 and 5. Okay. Now let's try to form the R cycle here. What is going to be the R cycle? This is 1 is mapped to 3, 3 is mapped to 5, 5 is mapped to 4, 4 is mapped to, okay wait, I want to give you an example where all of the images are going to distinct elements. Let's say this and this. Okay. Now again, 1 is going to 3, 3 is going to 2, 2 is going to 5 and 5 is going to 4 and 4 is again going to 1. Clear? We can represent this permutation in this form, which is known as 5 cycle. Why? Because there are 5 elements in it. So 5 elements implies it is a 5 cycle. But you might be thinking that if you are taking an element from S5, it is always going to have 5 elements. Then what is the point of calling it 5 cycle? Take an example for that. Now try to form a R cycle. Starting from 1, 1 is going to 3, 3 is going to 2 and 2 is going to again 1. So this cycle ends here. Now again what is happening? 4 is going to 5 and 5 is going back to 4. So here we are getting 2 separate R cycles for one permutation. For one function we are getting 2 different R cycles, right? And this representation is known as cyclic decomposition. आप इसको एक नंबर के इक्वेशन में भी कह सकते हैं दैट व्हाट इज द साइक्लिक डिकम्पोजिशन फॉर दिस परमिटेशन, दिस इज गोइंग टू बी 3 + 2. ठीक है, वो भी कहा जाता है, बट बेसिकली डिकम्पोज कर रहे हो आप, क्या कर रहे हो? सेपरेट कर रहे हो और गिवन परमिटेशन इन टर्म्स ऑफ आर साइकिल. सो दिस इज नोन एज योर साइक्लिक डिकम्पोजिशन. नाउ व्हाट इज दिस? दिस इज एन 3 cycle, right? And this is known as a 2 cycle. Now a cycle with length 2 ही हो गई ना उसकी, is also known as a transposition, the significance of which we will be taking up afterwards. What is the importance of transpositions? फिलहाल के लिए just understand the cycle which is of a length 2 is known as a transposition. Now finally one more example. Try to write the R cycle for it. 1, 3 and 2, and this cycle closes here. Why? Because 2 is going back to 1. Now 4 is being mapped to 4. That means this is a cycle of length 1 only, right? And 5 is being mapped to 5. But there is no point of writing 4 and 5 here. Why? Because 4 is going to 4 only and 5 is going to 5 only. So उनका होना ना होना बराबर है. Why? Because their happening is of no consequence. It is not going to make any difference in the any kind of permutation, right? So that is why यहाँ पे we can write it as just 1, 3, 2, and we know that this element belongs to S5, then we can say that 4 is being mapped to 4 and 5 is being mapped to 5. It can belong to S6 as well. In that case, what is going to happen? 6 is going to map to 6. Clear? Now, this is going to be again a 3 cycle, right? Now, just understand one thing. Yahan pe we saw one example where f dot g was not equal to g dot f. Clear? But if I multiply 132 by 45 and if I multiply 45 by 132, I'm going to get the same permutation. Why? Because they do not have any elements in common. They do not have any elements in common. That means the separate permutations, these separate cycles do not have any similar elements in them. That is why they are going to give me the same output every time. That means when the cycles are disjoint, that means they do not have any same elements, they are going to give me the same answer. That means in these cases f dot g will be equals to dot. Clear? So we can write a result here, or you can just write it as a note that the cycles or the product of cycles is same where they have no common element. Clear? Also, जहाँ पे elements common है, for that we have seen an example. यहाँ पे we saw that 1 2 3 4 1 2 3 4 are common and उनके images different है but the elements are common. तो यहाँ पे f dot g is not equal to g dot f. Clear? तो आज we are just going to see up till here only. ठीक है? SN हमने समझा that what kind of a group it is. ठीक है? In the next lecture we are going to be taking up order of elements. पहले we will be understanding that what order means. पहले हम बेसिक छोटे वाले ग्रुप्स को देखेंगे. लेट्स से ग्रुप ऑफ रेसिड्यू एंड देन यू हैव डाइहीड्रल ग्रुप्स एंड ऑल दैट. उनके सबके एलिमेंट्स को देखेंगे, पहले ऑर्डर को समझेंगे एंड देन वी विल कम टू ऑर्डर ऑफ SN group, the order of elements of SN group. All right, so that's all for today. We'll meet in the next lecture.